Hello everyone, my name is Walter. Today I will talk about our paper, ECC.fail, running Rowhammer attacks on DDR4 servers with ECC memory. If you look inside your computer, you'll find a motherboard with CPU and memory on it. Those two parts actually interconnected with each other and they talk to each other for your computer to work. So our work is a Rowhammer attack on DRAM. Before I can talk about what is a Rowhammer attack, let me first introduce how DRAM works. Let's look inside a DRAM chip. You'll find a 2D array of capacitors, or we call DRAM cells. The data are actually represented by whether there is charge or not in each DRAM cell. For example, if there's charge, the data is 1. If there's no, the data is 0. The CPU actually talks to DRAM by sending different DRAM commands. In our talk, we'll mainly focus on two of them, the row activate command or refresh command. So let's say the CPU wants to read some data from DRAM. You first activate a row by loading it into the row buffer. Then part of the row can be transferred into CPU. Before the CPU can read some data from another row, it will first pre-charge the row or close the row back into the DRAM cells. Further, since we know capacitors will gradually lose charge by itself, therefore CPU needs to send periodic refresh command to let DRAM select certain rows to refresh in order to keep the data integrity. DRAM actually does this by activating the row and recharging it back into the DRAM cells. So let's talk about what is a Rowhammer attack. If we activate two rows, for example, row 2 and row 4, very quickly, so we found that the row in between, in our case row 3, the cells of it will lose charge very quickly. This can be a problem if the charge goes below the threshold of determining 1 or 0 before it can be refreshed. In this case, we'll get a bit flip. Rowhammer bit flips can be exploited maliciously to get several bad things, such as root access, read or write memory, which is read or write memory of other processes, or even browser Rowhammer attacks. So for now, we have been talking about Rowhammer attacks on consumer computers. What about servers? It turns out that servers have something called error correction code, or ECC capability, that makes it more resilient against Rowhammer attacks. Let me explain how this works. So for example, let's say there's a Rowhammer bit flip and the CPU sees it. So the ECC logic will be able to detect the bit flip, correct it, and write the correct data back. Further, if there are 2 or more flips and the CPU sees it, although the ECC will not be able to correct it, it will simply crash the machine, preventing anything bad from happening further. So in either case, we cannot simply have Rowhammer attacks on DDR4 servers. So in our paper, we give the first Rowhammer attack on DDR4 servers with default configuration. What we actually achieved is we can get Rowhammer bit flips in average 2.5 hours and break RAC signature in average of 10 hours. So to get our results, we actually are faced with 4 challenges. First, since there's no prior research on DDR4 server DIMMs, we need to get some bit flip using Rowhammer on DDR4 server DIMM. After that, we need to recover the ECC matrix to know that where to flip so that we can bypass ECC. Thirdly, we need to find a way to template the DIMM to find those usable bit flip locations online without crashing the machine. Lastly, we need to combine all the previous steps and build a practical end-to-end attack. Now let's talk about our first challenge, getting some bit flips using Rowhammer on DDR4 server DIMMs. So actually there's no Rowhammer research on DDR4 server DIMMs, and thus we do not know whether we can get flips and how to get flips on those DIMMs. To solve this, we analyzed the Hynix server DIMMs on FPGA to find some effective hammering patterns. So using FPGA, we made our first observation that Hynix DIMMs actually use sampling-based TRR. So TRR stands for target row refresh, which is a mechanism employed by the DRAM vendors for Rowhammer mitigation. So the sampling-based TRR actually prevents Rowhammer bit flips by randomly sample one possible aggressor row actually, from all the row activate commands between two refresh commands. For example, if an attacker wants to get some Rowhammer bit flips by quickly activating row 2 and row 4. So the TRR logic will be able to randomly sample one of the rows, for example, row 2, from all the row activate command. And then after the TRR logic sees the next refresh command, we will proactively refresh the two adjacent rows that is adjacent to the current row being sampled in the TRR logic. In this case, row 1 and row 3. Therefore, the TRR can prevent Rowhammer bit flips from before it could happen. However, we also observed that the TRR sampler on those Hynix DIMMs are actually biased. This means that the TRR logic is much more likely to sample the several row activate command right before a refresh command. This is very bad from a defender's perspective, because a potential attacker can simply bypass the TRR by access a real dummy row right before a refresh command. And in this way, the TRR logic will only refresh the rows adjacent to the dummy row, which is not the real victim. And the real victim is likely to have bit flips. Now let's move on to our real machine. We first disable the ECC checking mechanism on our test machine, and then implement our Rowhammer attack program using native code with proper refresh synchronization. We actually get more than 100 flips per row on the real machine. So after getting enough flips on the DDR4 server DIMMs, we proceeded to recover the ECC matrix so that we can know where to flip to bypass ECC. Now let's take a closer look at how ECC works. So if this eCPU wants to write and cache the data into memory, ECC logic will first calculate some check bits corresponding to the data, which provides redundancy for errors. And to store those check bits, compared with the normal consumer DIMMs, the ECC DIMMs actually have extra chip to store them. Those check bits are very important for us to recover the ECC matrix. However, this whole ECC calculation process is transparent to the software, so we cannot directly read the check bits. Therefore, we use a logic analyzer to capture DRAM bus traffic to observe the check bits. Here's a picture of our logic analyzer setup. We use the DDR4 interposer to intersect the communication between CPU and memory. Here's an example of the data we captured. From the data, we can see the address of the command, the actual command, the data in the command, and most importantly, the check bits corresponding to the data. After we recovered the ECC matrix, we find that the code size of the ECC is 64 bytes to 72 bytes. The code distance is being surprisingly low, that is only 4. So after we recovered the ECC matrix, we now need to find a way to be able to find those useful bitfield locations on a real server without crashing the machine. So until now, we have been hammering on the real machine with ECC checking turned off. So if we turn on ECC and hammer with our current primer program, it's very likely that we will trigger 2 or more flips in a cache line that will crash the machine. Therefore, to solve this, we observed that ECC is very good at correcting single bit flip. And also, Rowhammer bit flips are dependent on data. Therefore, we opt to template only 1 bit at a time. We will set the data of the victim row to be the same as the data of the aggressor row, except for 1 bit. This will cause that bit much more likely to flip than any other bits. It's okay even if it flipped, because ECC will still correct it and the machine will not crash. So now we have a way to template bit by bit. However, we still need a way to detect whether the bit is flipped or not, because if the bit is flipped, it will be corrected by ECC, and the data readback is still the same. What we observe is that Intel memory controller will replay DRAM read when it encounters data corruption with bit flips. This means that if the CPU sees the bit flip, before the ECC will correct it, it will retry the read from the same location several times more to confirm the bit flip is actually present. If it is, it will correct it and read data back. That will make the access latency to the cache line with bit flips much longer than the access latency to the cache line without. In this way, we can have an access latency side channel to detect whether the DIMM is flipped or a bit is flipped or not. Now, our last challenge is to build a practical end-to-end attack. Let's recall what we get from analyzing the ECC matrix. We know that if we have 4 flips at a certain location in the cache line, the ECC logic will simply think there's no error, we get the ECC bypass. However, we find that it's very hard to find those 4 bit flips at useful location. Therefore, we want to see whether we can lose the requirement for ECC bypass. What we find is that the Intel server we tested actually supports chip-queue error correction capability. This means that even if a chip on the DRAM died, for example, it provides some random garbage data, the ECC logic on the server are actually still able to correct the bit flip or correct the data to keep the server running. So it turns out that we can exploit the chip-queue error correction capability on Intel CPUs to assist our attack. I will explain how this works. So for example, we have a DRAM with 18x4 chips from chip 0 to chip 17, and we have some 4-bit bypass templates. If we analyze the bit distribution of each template across chips, we will see some of them span across 2 chips with 2 bits in each chip, and some of them span across 3 chips with 2 bits in one chip and 2 other bits in 2 other chips. We know that from the code distance, if we hammer the template and 4 bits of them all flipped, we will get a bypass without error. What's more interesting is that if we only hammer the 2 bits in 2 different chips and both of them flipped, the CPU actually has 2 different views on this. It could be either the chip 0 has error, or the chip 1 and chip 2 both has errors. It turns out that the Intel CPU with chip-queue capability will think chip 0 has error, and will correct it by flipping the 2 bits in the chip 0. And that will let us to have a 4-bit bypass with only flipping 2 bits. That can make our end-to-end attack practical. Finally, we are able to build a practical Rowhammer end-to-end attack. The first step is to recover the DRAM TIR and the CPU ECC matrix. This is done offline. Then, on the real victim server, we use Rowhammer to tamper the DIMM to find out any useful location for ECC bypass. We use the timing side channel to detect single bit flips. The next step is to let the victim program to place its memory on the real victim DRAM row. We are using a technique called DRAM memory allocator massaging. So let's take a closer look at how memory allocator massaging works. So from the CPU side, on each CPU core, there is a current running process. And for Linux kernel, for each CPU core, it has a free page pool containing recently freed pages for the current process to use. On the physical memory side, the OS will divide memory into many pages. In our case, since the attacker is doing DIMM templating, it owns many pages that are actually stored in DRAM across several rows. So to let the victim program place its memory on the victim DRAM row, the attacker process will first voluntarily free the pages that it owned, that are also corresponds to the victim DRAM row. Then we will expand the victim program and immediately stop execution to let the victim program run. Then the victim program will try to map some pages, which will get the recently freed pages from the free page pool, which are actually lies in the victim DRAM row. After wait for some time, the attacker process will start execution and continue to trigger Rowhammer bit flips on the victim row. Finally, the attacker process will use Rowhammer to trigger bit flips on the victim memory. In our case, it's the RSA public key. Then the attacker can factorize the flip RSA public key to forge RSA signatures. In summary, we can get a Rowhammer payslip in an average of 25 hours and break RSA signature in an average of 10 hours. And that brings my talk to an end. I'm Wang. Thank you for listening. Feel free to check our project website and lab page.